guys, and thanks for joining me today here at NASA at Home, where we bring NASA home to you. You can check out more of our online activities at NASA STEM at Home for students. My name's Lindsay Thornton, and I'm an education specialist at NASA Langley Research Center in Hampton, Virginia. And today is all about sound and aeronautics. Now, you may be thinking to yourself, but it's NASA, and everyone thinks of spacecraft and astronauts and going to the moon. And those are all great, but we are the National Aeronautics and Space Administration. And we are innovators in the world of new designs and experimental aircraft. Our newest, the X59 Quest, is just inside. Let's take a look.
NASA's newest experimental airplane, the X59 Quest, is designed with quiet supersonic technology and is intended to help open a new era in faster-than-sound air travel over land. Now under construction by Lockheed Martin Aeronautics Company, the X59 is designed so that when flying supersonic or faster than the speed of sound, people on the ground will hear nothing more than a sonic thump, if anything at all.
The X59 is about the length of a professional basketball court and just over half as wide. It's got a really long nose, an engine on top, highly swept wings, and a body or fuselage that's been carefully designed so that the shock waves sound like a gentle thump instead of something much louder.
Once fully tested and pronounced safe to fly, the X59 will begin making supersonic flights over select communities to measure residents' reactions to any noise they might hear. The scientifically valid data gathered from these community overflights will be presented to regulators who will use the information to come up with new regulations based on noise levels that will enable commercial supersonic flight over land. So, just how will the X59 lower the sonic boom to a sonic thump? To understand this, you must first know what sound is and how it travels. Every sound we hear is produced by vibrations. These vibrations create sound waves, which can move in all directions through materials like solids, liquids, and gases. A sound wave is a compression or longitudinal wave, where the disturbance moves in the same direction as the wave. Check out this example using a stretched slinky. As the wave moves through the slinky from left to right, the disturbance will also move from left to right, parallel to the wave. The parts of the wave where it compresses are called compressions. A compression is a point where the waves are most compact. The parts of the wave where it stretches, or where it is least compact, are called rarefactions or expansions. Can you see the alternating pattern of compressions and rarefactions? Now let's look at some other characteristics of a sound wave. To determine the wavelength on a longitudinal wave, measure the distance between compression to compression or rarefaction to rarefaction. The frequency is the rate of vibration or the number of compressions or rarefactions that pass a point in a fixed amount of time. In a sound wave, increasing the rate of vibration increases the frequency, also increasing the pitch. The amplitude of the wave is the maximum height of the wave and directly determines the volume or loudness of sound. An increase in amplitude corresponds to an increase in volume. As sound waves travel through solids, liquids, and gases, they move the molecules, which transfers energy and causes the molecules to collide in the direction the sound is moving. As sound waves travel, they lose energy, which is why you can only hear sounds up to a given distance.
So knowing about how sound travels is very important to NASA scientists and engineers as we design supersonic aircraft. Perceived levels of noise of the sound waves reaching the ground can be 105 decibels or higher. In other words, a typical aircraft traveling at supersonic speeds is about as loud as a rock concert. The X59, however, is designed to be much quieter. We expect the X59 to reach perceived levels around 75 decibels in supersonic flight, which is a little bit quieter than closing a car door. Generally, commercial aircraft fly at altitudes of 36,000 to 41,000 feet. The X59 will travel at approximately 55,000 feet above sea level. At this altitude, the X59 will be flying at a height roughly 44 times higher than the Empire State Building and nearly twice the height of Mount Everest.
Now that you learned how sound travels, we've got an activity that you can do at home with materials that you can find around your house. So to start, you'll need 2 cups, whether they're plastic, paper, or styrofoam, it doesn't really matter. Anything will work. And you'll need an empty paper towel tube. You can also use a toilet roll tube as well if you don't have a paper towel tube. You're going to need some scissors, a pen or a marker, and if you'd like, you can also use some tape. Now you will need a phone or similar device that can play music or sounds of some kind. So the first thing I'm going to do is we're going to essentially build a little speaker system for your phone, but out of these simple homemade materials. So I'm going to trace my phone on my paper towel tube. I'm going to trace around the end of my phone so that I have a nice line to cut out, like so. So I'm going to cut this out, and then I'm going to make sure that my phone can easily fit in that slot and slide in and out, because we're going to be listening to how the noise or the sound varies as we slide our phone in and out. Okay, so we're going to want to cut that out. Then I'm going to want to take the end of my paper towel tube and I'm going to want to trace it onto my cups. So I'm going to take my marker and I'm going to trace around the edge of my paper towel tube so that I have 2 circles, and we want them in about the same place on our cups. We want to be able to keep everything very nice and even. So I'm going to want to cut those 2 holes out as well. Now once I've cut my holes out of my 2 cups and my slot out of my paper towel tube, I can put everything together. So I'm going to take those cups and I'm going to slide them on the ends of my paper towel tube so that they're facing the same direction. And then I'm going to cut that hole out, and like I said, we're going to make sure my phone can slide right in there just like that. Now I have a little speaker system. Now if you want to, if you're worried your cups are a little loose, you can always put a little tape on the bottom to hold them in place. Now you'll notice on the inside, my cup is only so far so that we allow room for the sound to come out of the paper towel tube. We don't want to push our cups all the way in, otherwise the sound won't be able to escape from the paper towel tube. All right, so once we have this, we can give it a try. So what I'm going to do is I'm going to turn on something on my phone, maybe my favorite song or some noises, some sounds, and then I'm going to slide my phone, making sure I have the speaker end going into my slot. I'm going to slide it in and out. And I'm going to listen and hear the difference between when my phone is in the slot and all of my sound is being directed in the same direction. Those sound waves are being pushed together so that we amplify that sound. But when I pull my phone out, the sound waves can go in all directions. And so it's not as loud to our ears. It doesn't amplify the sound. So give that a try and see the difference for yourself. And so now you've got a very cool, very easy to make speaker system. So if you don't have one at home, you can use this and you can take your phone outside while you're playing in your yard or up in your room, and it'll help you amplify the music you're listening to or the songs, whatever you happen to like. For my scientists out there, you can use a free sound meter app or decibel meter that you can get on your phone. You will need 2 devices in order for this to work, but it will allow you to take real-time data and see how well your amplifier is working. All right, great. So we've shown that we can amplify sound. What if we want to go in the other direction? Let's pretend that our 2 cups are 2 jet engines, and we want to quiet them so that we don't disturb the people and animals in our flight path. How would we do that? Well, a great example of quieting a very loud noise is our newest experimental aircraft, the X59. Let's go check it out.
We are surrounded by sound every day. From household sounds like dogs barking and people talking, to noise pollution from highways, industry, and planes, our days have gotten very noisy. NASA is working to reduce some of these unwanted noises. As a leader in aeronautics research, NASA is working to reduce the sounds produced by aircraft. The Low Boom Flight Demonstration, a NASA aeronautics mission, includes the design, building, and testing of the X59 Quiet Supersonic Technology Aircraft, or X59 Quest for short. The X59 will be able to fly at supersonic speeds, faster than the speed of sound, without producing a loud sonic boom. But what is a sonic boom? A sonic boom is the thunder-like noise a person on the ground hears when an aircraft or other type of aerospace vehicle flies overhead faster than the speed of sound or supersonic. Picture an aircraft flying through the air. As the aircraft moves, it pushes air out of its way, continuously creating sound waves. These sound waves, or air pressure waves, move away from the aircraft in all directions at the speed of sound, like ripples that form by dropping a pebble in a pond. By increasing the aircraft speed to supersonic, or faster than the speed of sound, the air pressure waves begin to pile up ahead of the airplane and compress, forming shock waves. These are similar to waves that pile up in front of a boat as it moves through water. In the air, the shock waves will move out and away from the aircraft. This creates a sudden change in pressure. The change happens so quickly that when the energy from the shock wave reaches our ears, it's heard as a loud crack of a sonic boom. So how is NASA trying to quiet the sonic boom with the X59? Let's find out from an X59 NASA engineer.
Well, the X59 is designed to generate a quiet sonic boom when it flies supersonically. Traditional airplanes that fly supersonically, such as the Concorde or military jets, develop a very loud sonic boom as they fly over the ground. It's very disturbing to people on the ground, and that's a big impediment to being able to just fly commercially all the time supersonically. So this airplane is a demonstration of a capability that we think we've developed to be able to shape the airplane such that it will not generate that loud sonic boom. And so if you look at a picture of the airplane design, you'll see that unlike a normal airplane, it's very long and slender. And the reason for that is to be able to shape the volume distribution and the lift distribution over the airplane in such a way that the shocks don't all coalesce into a very strong front and rear shocks that make that loud sonic boom. The airplane is designed to fly at a higher altitude for a number of reasons, one of which is the distance away from the ground reduces the noise from the sonic booms. So higher, farther away, it would be quieter. The other is, of course, that the airplane is designed such that the lift distribution over the airplane is what we need at a given angle of attack. And the angle of attack is the wind angle going into the airplane, how it touches the airplane. And so to get that angle correctly at the Mach number we want to fly at, puts you up at 55,000 feet, mid-50s. So the biggest challenge historically has been just in the capability of being able to analyze how the airplane is going to act. We've recently developed the tools to be able to predict how the sonic boom will be produced on the airplane and to be able to trace that to features on the airplane. And then that allows us to design the airplane like you see in the picture, the long, slender airplane that then develops the quiet sonic boom.
So the X59 will quiet the sonic boom to a sonic thump. But what about the planes that you and I fly on every day? How do we quiet their noise? Have you ever heard of a chevron? Probably not, unless you're really into aircraft. But a chevron is a noise-reducing technology that NASA helped to develop and is now being used on commercial jet engines. The noise we hear from jet engines mainly comes from the turbulent air created by two streams of air, one hot and one cold, mixing at the back of the engine. The air coming out of the jet engine itself is extremely hot, while the air flowing around the outside of the engine case is much cooler. When the stream of hot air leaving the inside of the engine meets the stream of cooler air from the outside of the engine, the air becomes turbulent and noise happens. NASA discovered that the chevrons can smooth out the point where the two airstreams meet, reducing turbulence and therefore noise. Alright, let's get back to our amplifier. Remember we said that we were going to pretend that our two cups were two jet engines. And how are we going to reduce the noise from those two jet engines? Well, that's up to you. I challenge you to build two devices to fit on the end of our two cups that will help reduce the noise. But you can't completely block the openings, otherwise our jet won't be able to fly. There won't be any thrust. You can use anything you can find around the house that Mom gives her okay to. Check your recycle bin, things that are being thrown out, and get creative.
Did you know that NASA engineers reuse and repurpose materials when designing new aircraft too? The X59 Quest, while a brand new experimental aircraft, has components from other retired aircraft, some major and some minor, including the landing gear from an Air Force F-16 fighter, a cockpit canopy from a NASA T-38 trainer, a propulsion system part from a U-2 spy plane, and a control stick from an F-117 stealth fighter. Reusing parts is common to NASA when designing new aircraft and spacecraft, as it saves time and money.
Now once you've created your devices, give them a try. Did they quiet the noise coming from your amplifier? If so, it's a success. Just remember to try it a couple times to be sure of your success. Even better, use your sound meter app to measure the decibel level to see if you've really quieted the noise coming from your amplifier. Now remember, as a scientist, even if our device works well, we always want to improve. Is there some way you could improve your device? Aha! Once you have an idea, try it out. And then, once you're done, find a family member and tell them all about it. How you built your device, what you were thinking when you made your improvements, and remember that a real scientist has to be able to communicate their research. So make sure you explain clearly and thoroughly.
Now that you've learned a little about the X59 and how sound travels, let's check out more of NASA's X-Planes over the years.
It's one small step for man, one giant leap for mankind.
History is about to repeat itself. Over the past 7 decades, the nation's best minds in aviation have designed, built, and flown a series of experimental airplanes to test the latest imaginative and cutting-edge ideas related to flight. Short wings, long wings, delta-shaped wings, forward-swept wings, scissor wings, big tails, no tails, high speed, low speed. Individually, each of these pioneering aircraft has its own story of triumph and setback. Together, they are known as X-Planes.
Each of those X-Planes has an interesting story all of its own. They've all made an incredible contribution to our understanding of flight, and X-Planes are really cool.
On October 14, 1947, Air Force Captain Chuck Yeager climbed into the bright orange, glamorous Glennis and flew the X-1 into its moment in history. The Bell X-1 was the first plane to fly faster than the speed of sound, thus breaking the sound barrier. Perhaps of all the X-planes NASA has been associated with, None was more cutting edge and became more famous than the X-15 rocket plane.
The X-1, it's the most famous because it was the first to go supersonic. But the X-15, it was the most productive of our X-plane programs.
Flown between 1959 and 1968, the winged X-15 reached beyond the edge of space at hypersonic speeds, trailblazing design concepts that contributed to the development of the Mercury, Gemini, and Apollo-piloted spaceflight programs.
It's one small step for man, one giant leap for mankind.
History is about to repeat itself again, and humans will take another giant leap. NASA is building a new generation of X-planes. The first all-electric aircraft, the X57, will increase fuel efficiency, significantly reduce carbon emissions, and reduce unwanted noises. The newest X-plane, the X59, will be an aircraft that flies at supersonic speed. But instead of creating the annoying sonic boom, creates a quiet sonic thump.
The X59 aircraft is an exciting addition to a long history of X airplanes, including the X1 and the X15. NASA is working with Lockheed Martin to design, build, and flight test the X59 aircraft. It's going to be about 97 feet long, fly at a Mach number of about 1.42, which is roughly around 900 miles an hour. It's got a long nose, engine on top, highly swept wings, and a very carefully shaped fuselage to enable that low boom flight that we require for this airplane. There's really three phases on the low boom flight demonstration mission. The first one is we need to make sure that the airplane is safe to fly and to fly in the United States airspace system at about 55,000 feet. Second of all, we need to do validation flights to show that the airplane can fly in a variety of flight conditions and atmospheric conditions. And then the third phase is really this community response data, where we go out and get the data and provide this data to regulatory agencies such as the FAA so that they can lift the ban on commercial supersonic flight.
The success of the X59 could be the next giant leap for mankind here on Earth. This means one day in the not too distant future, you may be flying on a supersonic commercial flight over land, getting where you need to go in half the time. How cool is that? Remember, NASA is with you when you fly.
Thanks for joining us, and don't forget to tune in next time when we bring NASA home to you. There's also more activities you can do online at NASA STEM at Home. See you next time!